Assalamu alaikum warahmatullahi wabarakatuh, everyone. My name is Muhammad Bashar, and today my group is going to review a very fascinating paper titled Speech Recognition in Landslide Predictive Modeling, a Case for a Next Generation Early Warning System. So, from the title itself, we might wonder, what does speech recognition, like Siri or Alexa, have to do with landslide? That is exactly the question that this research tries to answer. For my part, I will give a bit introduction and the summary of the paper. What's the objective of the paper? What were they trying to achieve? What problems were they trying to solve? And I will give a bit summary of the method and the result. But for more detailed breakdown, it will be explained by my teammates. So now let's dive into the paper. So first, let's look at the problem they are trying to solve, right? The traditional method to predict landslide or traditional landslide early warning systems usually look at rainfall in a very simple way. Okay, they take all the rain that fell over a few days and they mix it or they squash it into a single number or a total sum. In math, we call this a scalar value. The authors of the paper argue that this kind of approach is a mistake. Why? Because rain is not static. Rain has a rhythm. Heavy rain followed by a pause is very different from light rain or a steady drizzle, even if the total amount is still the same. By squashing the data into one number, we lose all the rich information about time. Time is a very important variable. So this is where the novelty or the genius of the paper comes in. The authors realize that rainfall data looks a lot like sound waves. You can see in the diagram we show here. So when a computer recognizes speech, it doesn't just measure how loud we shout, for example. It actually analyzes the vibrations of our voice over time to understand the words. So the authors of the paper, they propose a new idea. What if we treat rainfall charts like sound waves? What if we use the same deep learning algorithms used for speech recognition to listen to the rain and predict landslides? So to test this hypothesis or their idea, they focus on Turkey's demographic, covering a huge dataset of 13 years from 2008 to 2020. They use an algorithm called LSTM, or long short-term memory. This is a type of neural network designed to remember sequences of past events, which is perfect for analyzing 60 days of daily rainfall rather than just a single sum or total. Why 60 days? Because 60 days is the most optimal duration to really study the rain and predict landslide without sacrificing any data loss or accuracy. So a bit of summary of the results. Did the method work? Actually, the results were very impressive. The study showed that listening to the full rainfall signal increased prediction accuracy by approximately 20% compared to the traditional methods. Their model achieved accuracy score of 92%, proving that timing of the rain matters just as much as the amount of the rain. So in summary, this paper successfully introduces a third dimension, which is time, into landslide prediction, paving the way for much smarter early warning systems in the future. So now my next teammate will dive deeper into the methodology and algorithms used. Thank you.
My name is Mazam Jamil, and now we move to the methodology. The first one is data collection method used in this speech recognition on the landslide. For the predictive model, the sourcing from the digital media's report, printed local news, and various research papers on multiple backgrounds. So how they utilize these sources? First one, the search keywords, landslide, in the Turkish language, because this research is focusing on the Turkish landslide issue. And the second one, they verify the report and the sources they use by utilizing optical images from Project Lab, which is from Google Search, Telescope, and Rapid Eye. So the algorithm used in this research is they're using long short-term memory network or LSTM, which it has three gate function. The first one is input gate, which is basically to memorize new information and update the input gain. And second one is forget. forget gate. Forget gate is to determine if previous input should be remembered or forget. So the last one is output. Output gate is to control the output activation and hidden memory state. And then we move to model implementation. They're using Python, which is powered by Keras. So the rainfall data is collected every day for everyday occurrences between 2008 and 2020, lasting for 13 years. So for this project, they handling the noise by removing the landslide point if the rainfall was zero, because they want to adopt reliability. To improve the accuracy, the researchers adding extreme values such as heavy rainfall but no recorded landslide upon that day. Why do we need to add the extreme values? The extreme values is important because it can help the model to learn the difference between the pattern of the rainfall between normal downpour and actual heavy rainfall that possibly could trigger a landslide. So, extra note here, you know that there is a subtle sounds different between a rainfall on a slope ground and open flat area. It is because of the angle of impact and the distribution of force on the ground. And then we move to model validation. The researchers use Stanford cost validation on a balanced dataset, and they also compare their model with a traditional early warning system, which are from the past research from Segoni and etc. So for the model performance assessment, they utilize a UC, a Fosco, and Cohen-Kappa coefficient so that the model could be more reliable and accurate, representative of the landslide predictive modeling in Turkey.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adam Mahami with metric number 2319255. Today I am going to present analysis of result. We focus on two things here. The first is reliability. As we can see, the proposed method achieved an AGC score of 0.920. To put that in perspective, the traditional method usually hovers around 0.75. This big difference proves that the LSTM approach is much more reliable for this task. Next, regarding the data sufficiency, the dataset analyzed 30 years of data across the Turkey. While the coverage is great, the spatial resolution of church data is about 0.05 degrees, which detected the 5 kilometer grid size. This is a big cost. It works well for general areas, but it does mean the model might struggle to give precise alerts for specific individual slopes. Now, let's look at the figures. Okay. If we focus on figure 5 on the left, we have a direct comparison. The black line represents the proposed method, and the orange line is the traditional method. As we can see, across every metric, whether it is AUC, F1 score, or kappa coefficient, the proposed method consistently stays above the traditional one. It just performs better across the board. Then, moving to figure 6 on the right, we can see how the model reacts in a real-world scenario over the month of June. If we pay attention to the small graph at the bottom right, we will see a blue line representing precipitation. Around June 12th, there is a sharp spike in rainfall. Notice how the red line, the landslide probability, shoots up almost immediately in response. This is crucial finding because it proves the model is highly sensitive to sudden impulsive rainfall, which is exactly what we need from an effective early warning system. Finally, we move to conclusion. First, we achieved a 20% increase in predictive power compared to the standard intensity duration threshold over 60 days. Put simply, the neural network is much better at distinguishing between landslide and non-landslide patterns than the traditional methods. Second, we learned that detail matters. We found that continuous precipitation signals carry way more useful information than simple scalar approximations. In fact, when we try switching back to scalar values, the model's performance dropped drastically. This proves that if we aggregate the data too much, we lose the temporal dynamism or the timing context that is crucial for accurate predictions. And finally, the model is smart enough to handle rainfall spikes. It successfully captures the sudden impulsive spikes, allowing it to distinguish between the long-term rain that saturates the soil, the preparatory pace, and the short, intense storms that actually trigger the landslide. Alright, next is future suggestion. First, regarding forecasting, to make this truly useful in the real world, we suggest the next step is to retrain and test the model using forecasted precipitation data such as GeoSFP. Second, we need higher resolution. We suggest incorporating ground-based radar data to sharpen the image. This would improve the spatial resolution and allow for more precise localized alerts. And thirdly is typology. We suggest classifying the inventory by specific landslide type to fine-tune how the model interprets hydrological data for different terrains. So that's all from us. Thank you.